Welcome to section 2.3, sine and cosine functions. At the end of this section, you should be able to answer all these questions. What is a periodic function? What is the period of a function? What exactly is sine theta? And what is cosine theta? What is the UV coordinate system that we'll be using in our textbook? Why is r always positive? What implications are there if r is always positive? What is a parent function? What are critical points? And how do critical points assist us in sketching transformations? Alright, so let's talk about periodic functions. Here's this definition. The function f is a periodic function of x if and only if there is a number p for which f of x minus p equals f of x for all values of x in the domain. What that basically says is that our function repeats itself over a certain measurable distance. That smallest measurable distance that causes repetition is what we call the period of the function. Sine and cosine functions can be measured for any angle, not just the angles in a right triangle. So we're going to let UV be a point r units away from the origin on the terminal side of a rotating ray. So let's take a ray. We'll put it out here, and we're going to label that point where it ends u comma v, which means that we are u units horizontally and v units vertically. Giving us a distance r for this angle theta, r units away from the origin. So if we are going to calculate the sine of theta, that angle that we've drawn here, it would be defined by the vertical distance over r, and the cosine would be the horizontal distance away from the origin over r. If we rotate r around the origin, you can see that our horizontal distance and our vertical distance will change even if r remains constant. If we track that, we'll see graphs that are created that look like this. If you click on each of these graphs, you can see them being created on a website that I found. If you really want your mind blown, click on the fancy. To see how the sine wave is generated, we're going to take our ray r and rotate it around the circle and see what happens to the vertical distance from the horizontal axis. As you can see, it grows until it reaches a maximum, then shrinks until it's back on the horizontal axis, so a vertical distance of 0, and then it becomes negative as we continue our trip around the circle. Now let's look how the cosine wave is generated by measuring the horizontal distance for our reference triangle as we rotate r around the circle. As you can see, it starts at a maximum, hits 0, becomes negative, goes back to 0, and then finally returns to its maximum. So let's start by drawing a 147-degree angle in standard position. So that would put us in the second quadrant. And if we're going to draw the angle, again, we always start from the positive horizontal axis. So this is my angle theta, 147 degrees. Now I want to find the cosine of 147 and the cosine of the reference angle. To mark the reference angle, remember the acute, positive, angle attached to the horizontal axis. Let's find the measure. It's in the second quadrant, so the measure of our theta reference would be 180 minus 147, or 33 degrees. Now, let's find the cosine of 147 and the cosine of 33. Pull out our calculators. We want to check and make sure in our mode that we are in degree mode, not radians. We are. Now I'll simply ask for the cosine of 147. And I will get negative 0.83867, etc. Now let's take the cosine of our reference angle. That was 33 degrees. And here I get positive 0.83867. So rounded to 3 decimal places. So why is one negative and one positive? If we think about our horizontal distance from the origin for this angle, we'll see that it gives me a negative u value. And if we remember that r is always positive, for our actual angle, we are talking about a negative u over a positive r. For our reference angle of 33 degrees, if we were to draw a 33-degree angle, our u value would be positive. Hence, a positive value for the reference angle. Let's take a look at it from another perspective. The terminal side of angle theta in standard position contains the point 8, negative 5. So let's find that point. There we are. And that would put us right here. If we were going to sketch the angle in standard position from the positive horizontal axis to the terminal side. So there is theta. The sine of theta would be the vertical distance, which is negative 5, over r. To calculate r, we're going to have to use the Pythagorean Theorem. We know that this is 8, and this is negative 5, so r is going to be the square root of 8 squared plus negative 5 squared, which would be the square root of 89. The sine would be the vertical distance over r, so it turns out to be negative 5 over root 89. And the cosine would be the horizontal distance over r, or 8 over root 89. Our last example, we're going to create a new graph, y equals 4 sine theta. And we want to know what transformation of the parent sine function is this. Well, by the parent function, we mean the basic sine theta graph. So what we did to y equals sine theta was we multiplied it by 4. We multiplied the entire equation by 4, so that means that we are performing a vertical dilation, since we took the whole function and multiplied it by 4. So we would say a vertical dilation by a factor of 4. To sketch the graph, we identify key points where it would be easy to show this vertical dilation. So those points we call the critical points. Critical points where the function is equal to 0 or at a maximum or a minimum. Here at the origin, it's equal to 0 when we multiply by 4. We stay there at 0. We reach a maximum at 90 degrees of 1. But now we're going to multiply that by 4, so at 90 degrees, I'm going to move up and mark a point at 4. 1 times 4. At 180, we're at 0 again. At 270, I'm at negative 1, so now I drop down to negative 4. And at 360, I'm back to 0. 4 times 0 is 0. Now we play a game of connect the dots. And this would be our sketch. And there's our lesson.